Everything you see began with a single, impossible moment. We are going to the very beginning to explore 30 of the most incredible theories about the universe's first particles. By the end, you will have a front row seat to the greatest origin story ever told, understanding the wild ideas that explain how something came from nothing. Was our cosmos born from a collision of invisible membranes, or is it a hologram projected from the edge of reality? We will start with the familiar explosion and venture into realms where particles are vibrations, information, and even fragments of a previous cosmos. What do you believe sparked it all? The classic story begins not with a bang, but with a whisper of pure mathematics. Theory number 1, the Big Bang singularity, paints the ultimate starting line. According to this foundational model, our entire observable universe was once compressed into a single, incomprehensible point. This was a singularity, a condition where density and temperature reach values so extreme they become infinite, and our known laws of physics simply cease to apply. There was no space as we know it, and no time ticking forward. Everything was here in a state of pure, searing potential. This moment, the tiniest fraction of a second we call the Planck epoch, remains a complete mystery to science. It is a blank page in our cosmic history book, because the energies involved were so monumental that general relativity and quantum mechanics, our two best descriptions of reality, contradict each other completely. We cannot see past this wall. Then, in a process we call cosmic inflation, that singular point expanded faster than the speed of light. Space itself stretched, and as it did, it cooled. It was only after this rapid cooling, a mere sliver of a second after the beginning, that the universe became cool enough for the first particles to even be possible. From a swirling, opaque soup of energy known as a quark-gluon plasma, the most fundamental building blocks began to condense out, like droplets forming in steam. Quarks and gluons, the particles that would eventually bind together to form protons and neutrons, were not present at the absolute beginning. They were the first children of a cooling, expanding reality. So while the Big Bang gives us a powerful framework, it also presents us with its greatest puzzle, a door at time zero that remains firmly locked, hiding the true origin of everything. But that locked door hides an even stranger truth. If the Big Bang gave us the stage, then cosmic inflation wrote the first lines of the script. This is theory number 2, and it solves some of the most glaring puzzles the classic model left behind. Why does the universe look so remarkably similar in all directions? And why is space so incredibly flat? The answer lies in a fraction of a second of hyper-rapid expansion. A growth spurt so violent it stretched a subatomic patch of space into a volume larger than our entire observable cosmos. During this inflationary epoch, the universe was dominated by a strange energy field, often called the inflaton field. And like any quantum field, it was not perfectly smooth. It buzzed with tiny, unavoidable jitters, quantum fluctuations happening on the smallest scales imaginable. Here is where the magic happens. As space itself inflated faster than light, it did not just get bigger. It stretched those infinitesimal quantum ripples along with it, blowing them up from the quantum realm to the size of galaxies. These imprinted wrinkles in the density of the universe became the ultimate seeds. They were the first structures not made of matter, but of slight variations in the very fabric of space-time. Where a ripple created a slightly denser region, gravity had a tiny head start. Over billions of years, that speck of extra density pulled in more and more matter, eventually growing into a vast cluster of galaxies. The emptier regions became the great cosmic voids. So in a very real sense, the first particles of our cosmic story were not particles at all. They were these quantum whispers, frozen into the expanding universe, destined to become the blueprint for everything we see. Every star, every planet, every one of us, traces our origin back to a random jitter in a field that existed for less than a blink of an eye. That quantum blueprint needed a canvas, and the universe provided one of unimaginable ferocity. A microsecond after the beginning, our entire cosmos was not a collection of stars or galaxies, or even recognizable atoms. It was a single, seething ocean of raw potential. This is theory number 3, the era of the primordial quark-gluon plasma. Picture the hottest, densest substance you can conceive, a state of matter so extreme that the fundamental forces we know today were merged into one. In this primordial soup, the universe was completely opaque. Light could not travel freely because it was constantly being absorbed and re-emitted by a swirling chaos of the most basic building blocks, quarks and gluons. These were not yet locked inside protons and neutrons. They roamed free, a collective superfluid so dense that it behaved like a single, unified entity. For a fleeting moment, this was the entire universe, a blindingly hot plasma where the very concept of an individual particle was almost meaningless. Then expansion did its work. As the universe continued to swell and cool, it crossed a critical threshold. The temperature dropped enough for the strong nuclear force, which binds quarks together, to finally take hold. It was like a phase change, similar to water vapor condensing into droplets. The free-roaming quarks and gluons suddenly found themselves grabbed in groups of 3, bound together into the first stable composite particles, protons and neutrons. This moment, known as hadronization, marks the birth of the first tangible pieces of matter as we would recognize them. The opaque soup cleared, and the universe became transparent to the forces within it. This is not just theoretical. In places like the Large Hadron Collider, scientists recreate microscopic flashes of this quark-gluon plasma by smashing heavy ions together at nearly the speed of light. For an instant, in those detectors, we glimpse the universe as it was in its first fleeting moments, watching as a droplet of that primordial soup cools and condenses, giving us a direct window into the very first particle era. Yet the idea of a single, hot beginning is not the only story on the table. Some of the most radical theories suggest our entire experience of reality is a kind of magnificent illusion. This brings us to theory number 4, the holographic principle. Emerging from the depths of string theory and black hole physics, this concept proposes something almost unbelievable. Our rich, three-dimensional universe, with all its galaxies, stars, and people, might not be fundamentally three-dimensional at all. Instead, it could be a projection, a cosmic hologram, encoded on a two-dimensional surface that surrounds us at the boundary of space. Think of the hologram on your credit card. It is a flat, two-dimensional sticker, but when light hits it just right, it creates the stunning illusion of a three-dimensional image floating in the air. The holographic principle suggests our universe operates on a similar, but vastly more profound, scale. All the information needed to describe every particle, every force, and every event within our three-dimensional cosmos could be perfectly stored on a distant, two-dimensional shell, like the surface of a giant bubble. If this is true, it turns our understanding of the first particles completely on its head. The quarks and gluons that condensed from the plasma, the very seeds of matter, may not be the fundamental bedrock of reality. They could be secondary phenomena, emergent properties that arise from something more basic, information itself. In this view, the first particles were not tiny specks of stuff, but rather bits of data, like ones and zeros, etched onto the cosmic horizon during the universe's earliest moments. The three-dimensional world we experience, with its solidity and depth, would then be a kind of decoded message, a translation of that two-dimensional data into the rich tapestry of space and time. It is a theory that challenges the very notion of what is real, suggesting that at the most fundamental level, the universe might not be made of things, but of a cosmic code waiting to be read. But if the universe is a hologram, what is the screen it's projected upon? Another revolutionary idea suggests the fabric of reality itself has a granular, pixelated structure. This is theory number 5, loop quantum gravity. While string theory proposes tiny vibrating strings, loop quantum gravity takes a different path. It asks a profound question: what if not just matter, but space and time are also made of discrete, indivisible pieces? In this view, the smooth, continuous spacetime of Einstein's relativity is an illusion that emerges from a deeper reality, a reality woven from a vast network of tiny, interconnected loops. Think of the fabric of the cosmos not as a smooth sheet, but as an incredibly fine mesh, a tapestry of a trillion threads. Each thread is a loop of gravitational field, a fundamental atom of geometry. These loops, when woven together, create the volume and geometry of space itself. They are not inside space, they are space. This has a stunning implication for our origin story. In loop quantum gravity, the dreaded singularity of the Big Bang, that point of infinite density, cannot exist. There is a smallest possible size, a quantum of volume. So what happens when you rewind the cosmic film? The universe contracts down to this fundamental scale, but instead of collapsing into a meaningless point, the loops of spacetime reach a maximum density and then rebound. The Big Bang might not have been a beginning from nothing, but a transition, a big bounce from a previous, contracting universe. In this breathtaking scenario, the first particles of our cosmic story were not quarks or electrons. They were these quantized units of geometry themselves, vibrating and interacting as the previous cosmos collapsed, and then sprang back into a new expansion. The universe we inhabit could be one cycle in an eternal cosmic heartbeat, with the remnants of a previous universe transformed into the quantum seeds of our own. Yet another theory rewrites the ingredients list of reality entirely. If loop quantum gravity suggests space is woven from threads, then string theory proposes that the threads themselves are the fundamental substance. Theory number 6 introduces us to a universe not made of dots, but of music. In string theory, the most basic entities are not zero-dimensional points, but unimaginably tiny, one-dimensional loops or strands, vibrating in a space of many more dimensions than the three we experience. These strings are so small that if an atom were the size of our solar system, a string would be no larger than a tree on Earth. Their magic lies in their vibration. Just as a single violin string can produce different notes depending on how it is plucked, a fundamental string can vibrate in an almost infinite variety of modes. One specific resonant frequency might correspond to an electron, another to a quark, and still another to a photon, the particle of light. In this elegant symphony, every particle we have ever discovered is just a different note played on the same cosmic instrument. So what does this mean for the universe's first moments? In the extreme heat and density of the Big Bang, these strings would have been in a state of unimaginable frenzy. They were not yet vibrating as distinct particles like quarks or electrons. Instead, they existed in a highly energetic, unified state, a chaotic symphony where all possible notes were being played at once. The first things were these ultra-dense, wildly oscillating strings. As the universe expanded and cooled, it was like the concert hall growing quiet. The vibrations of the strings settled down into stable, distinct patterns. The chaotic noise resolved into the first recognizable chords, the specific vibrational modes that became the first generation of quarks, leptons, and force carriers. In this view, the entire history of our cosmos is the story of a cooling, calming vibration. The matter that makes up your body is not just ancient stardust. It is the echo of a specific harmonic pattern that was struck in the first fleeting moments of time, a note that has been ringing out for over 13 billion years. That cosmic symphony may have been a duet. While string theory reimagines particles as notes, another profound idea suggests every note we know has a hidden harmony. This is theory number 7, supersymmetry. It proposes an elegant, almost beautiful symmetry at the heart of reality, a fundamental partnership between the two great families of particles. On one side are the fermions, the particles of matter like quarks and electrons. On the other are the bosons, the force carriers like photons and gluons. Supersymmetry, often called SUSY, suggests that for every known fermion, there exists a heavier bosonic superpartner, and for every known boson, a heavier fermionic twin. The electron would have a partner called the selectron, a photon's partner would be the photino, and the familiar Higgs boson would be paired with the Higgsino. In the unimaginable heat of the very early universe, energy was so plentiful that these superpartners would not have been exotic rarities. They would have been abundant, created and destroyed in a frenzied thermal equilibrium alongside their standard counterparts. The cosmos was a perfectly balanced dance of matter and its symmetrical shadows. But as the universe expanded and cooled, that perfect symmetry broke. The superpartners, being much heavier, became unstable. They rapidly decayed away into the lighter, standard particles we see today. Yet their brief existence could solve two of cosmology's greatest mysteries. First, the lightest of these superpartners, often theorized to be a particle like the neutralino, would be stable and nearly invisible to ordinary forces. It would be the perfect candidate for dark matter, the unseen gravitational glue holding galaxies together. Second, the decay processes of these superpartners could have subtly favored matter over antimatter, explaining why we live in a universe of stuff and not just empty radiation. So in this view, the first particles were not just the quarks and gluons of the plasma. They were a complete, symmetrical set, a full cast of characters where every player had a heavier twin. Our familiar world is just the light, stable remnant of that grander, more balanced ensemble. A cosmic echo of a symmetry now hidden by the cold expanse of time. But even those vibrating strings might hide a deeper layer of structure. Could it be that quarks and electrons, the bedrock of our material world, are themselves composite? This is theory number 8, the realm of preons and subquark theories. If we think of particles as a set of Russian nesting dolls, the standard model reveals a beautiful set. But some physicists suspect there is a smaller doll still hidden inside. These hypothetical constituents have names like preons, rishons, or haplons, and they represent a bold idea that the particles we call fundamental are not the end of the line. They are built from something even more basic. In the unimaginable chaos of the universe's first instance, when energies were far beyond anything we can recreate, the cosmos would not have been a soup of quarks and leptons. It would have been a frenzied sea of these pre-particle entities. They would have zipped through the primordial fire, colliding and combining according to rules we can only guess at, like the pieces of a cosmic Lego set snapping together to form the first stable structures. A few preons of one type binding together might yield a quark. A different combination could produce an electron. In this view, the dawn of matter was not the condensation of quarks from a plasma, but the assembly of quarks themselves from a more fundamental substrate. The appeal is clear. It offers a way to explain why we have the specific family of particles we do, with their particular charges and masses. They are not arbitrary. They are the possible stable configurations of a smaller set of building blocks. Yet for all its theoretical elegance, this idea faces a formidable challenge, a complete lack of experimental evidence. Our most powerful particle colliders have probed to scales 1,000 times smaller than a proton, and quarks and leptons still appear to be point-like, with no internal structure. They behave as if they are truly fundamental. But many proponents argue we simply have not reached the staggering energies needed to crack them open. Energies that were commonplace in the universe's first fraction of a second. The search for preons remains a quest for a deeper truth, a suspicion that our cosmic nesting doll has one more, stunning layer waiting to be revealed. This search for a deeper layer leads to a cosmic scenario so vast it redefines the word collision. String theory's extra dimensions are not just curled-up tiny spaces. They could be vast arenas for entire universes to exist side by side. This brings us to theory number 9, the ekpyrotic or brane collision model, a radical alternative where the Big Bang was not a beginning from a point, but an event on a much larger stage. In this view, our entire three-dimensional universe is not all there is. It is a three-dimensional membrane, or brane, floating within a higher dimensional space called the bulk. Picture our cosmos not as an expanding balloon, but as an immense, flat sheet drifting in an incomprehensible void. And we are not alone. Other branes, other entire universes with their own laws of physics, could be drifting in this same bulk, separated by distances in these extra dimensions. The story of our beginning is not one of a singularity, but of a slow, cosmic approach. Our brane and another parallel brane, drawn together by a force across the bulk, move on a collision course over eons. When they finally meet, it is not a cataclysmic crash of planets and stars, because the stars and planets do not exist yet. The collision happens across the entire infinite surface of each brane simultaneously. The impact transfers an unimaginable amount of energy into the fabric of our three-dimensional sheet. This energy manifests as a torrent of heat and motion, igniting the rapid expansion and heating we call the Big Bang. In this model, the first particles of our universe were not born from a singularity's decay, but from the shockwaves of that collision. They were ripples and vibrations propagating across our brane, like patterns forming on the surface of a pond after a stone is dropped. The immense kinetic energy of the impact was directly converted into the seething quark-gluon plasma, from which everything condensed. This idea elegantly sidesteps the troubling singularity, replacing a mysterious starting point with a physical, though spectacular, event in a higher dimensional space. It suggests our cosmos is one page in a much larger book, and our entire history, from the first quark to the last galaxy, is the afterglow of a moment when two worlds touched in the dark. The collision of cosmic branes paints a picture of a single, dramatic birth. But what if our universe has no true beginning or end at all? Theory 10, conformal cyclic cosmology, proposed by the Nobel laureate Roger Penrose, offers a vision of eternity. It suggests our universe is just one chapter in an endless, repeating sequence, each called an aeon. In this breathtaking model, the distant future of one universe becomes the smooth, silent birth of the next. As an aeon like ours expands forever, all matter eventually decays, black holes evaporate, and even particles lose their sense of mass and scale. The universe becomes an almost featureless, cold, and infinitely vast expanse. But through a mathematical transformation, this vast emptiness can be reinterpreted as the hot, dense, and tiny starting point of a new Big Bang. The end becomes the beginning seamlessly. So where do the first particles of our aeon come from? They are not created from nothing. They are the transformed remnants of the most cataclysmic events from the previous cosmos, specifically, the collisions of supermassive black holes in its final stages. When these titans merged, they would have released unimaginable bursts of energy in the form of gravitational waves. According to Penrose, that energy did not just dissipate. It was imprinted onto the fabric of the new universe as it inflated. These imprints should appear in our sky today as faint, circular rings of slightly higher temperature within the cosmic microwave background, the afterglow of our own Big Bang. Penrose calls these features Hawking points, named for Stephen Hawking, and he claims we have already detected them in satellite data as mysterious, unexplained hotspots. If true, the very first seeds of structure in our universe, the subtle variations that grew into galaxies, were not random quantum jitters. They were cosmic fossils, the gravitational echoes of black hole collisions that occurred in a universe that existed before time as we know it began. Our entire reality could be a magnificent palimpsest, written over the faded story of a cosmos that came before. The endless cycles of eons suggest a cosmos that is profoundly old, but what if we could peer into its very first moment, into the fabric of reality at the smallest scale imaginable. At the heart of quantum mechanics lies a principle so strange it redefines the word nothing. The Heisenberg uncertainty principle tells us that on the tiniest scales, nature is inherently fuzzy. We cannot precisely know both the energy of a point in space and the time for which that energy exists. This creates a loophole in the laws of physics, a temporary loan of energy from the universe itself. Because of this, empty space is not truly empty. It is a seething, bubbling sea of potential, where particle-antiparticle pairs spontaneously blink into existence and then annihilate each other almost instantly. These are virtual particles, borrowing energy from the vacuum and paying it back before the universe can notice the debt. Now, shrink your perspective even further, down to the Planck scale, a distance so minuscule it is a trillion times smaller than an atom. Here, the very concepts of space and time break down. Space-time is not smooth. It is a turbulent, frothing chaos, a quantum foam. In this realm, the distinction between something and nothing becomes meaningless. The foam is a churning ocean of virtual particles, microscopic black holes and wormholes, all appearing and vanishing in a frenzied dance. This is Theory 11, the universe born from quantum foam. In the first sliver of the Planck epoch, the entire cosmos may have been nothing more than this foamy turbulence. The universe was not a point, but a probabilistic froth, a place where reality itself was a statistical possibility. Some cosmologists propose that our entire universe is the result of a single, staggeringly rare quantum fluctuation within this foam. A bubble of true vacuum, a region of lower energy, could have spontaneously formed, and instead of instantly collapsing, it was caught by the process of cosmic inflation. That bubble was stretched faster than light, its walls expanding to become the entirety of our observable cosmos. In this breathtaking view, everything we know, every galaxy, every star, every one of us, is the amplified echo of a random twitch in the quantum foam. Our existence is the ultimate statistical outlier, the one in an infinity chance that a quantum hiccup in the fabric of nothingness grew up to become everything. That random twitch in the quantum foam, if it truly happened, would have been governed by a single, perfect law. The ultimate quest of physics is to find that law, a single, elegant framework that explains every force and every particle. This is Theory 12, the dream of a theory of everything. It is the idea that in the universe's first, unimaginable moments, there was no distinction between gravity and the other forces. All of nature's interactions were one, a single, symmetrical superforce. The first particles in such a reality would not have been quarks or electrons as we know them. They would have been the simplest possible excitations of this unified field, pure expressions of a perfect cosmic symmetry. Picture a perfectly round, perfectly smooth ball resting at the peak of a hill. That is the state of perfect symmetry, but it is unstable. The slightest nudge, and it will roll down into a valley below. The ball is still a ball, but its position has changed. The symmetry is broken. This is precisely what happened as the infant universe expanded and cooled. The first nudge came almost instantly. As temperatures plummeted from trillions of degrees, the superforce could no longer hold its unified state. Gravity was the first to peel away, separating from the other three forces. This was the moment when space-time itself became a distinct entity. A fraction of a second later, the strong nuclear force which binds quarks together split off. Finally, as the universe continued to cool, the remaining unified electroweak force broke into the two distinct forces we know today, electromagnetism and the weak nuclear force. Each of these symmetry-breaking events was a cosmic phase transition, like steam condensing into water. And with each transition, the nature of matter itself changed. The simple, unified excitations of the initial field gained new properties, crystallizing into the diverse cast of particles that would fill the quark-gluon plasma. The Higgs field, which gives particles mass, is thought to have switched on during the electroweak transition, suddenly weighing down certain particles while leaving others, like photons, racing through the cosmos untouched by mass. So the timeline of our universe's first second is a story of increasing complexity born from broken symmetry. From a state of perfect, featureless unity, the cosmos cooled and fractured, giving rise to the rich tapestry of forces and particles that would eventually build atoms, stars, and us. The theory of everything is the search for that original, pristine equation. The mathematical melody that was playing before the symphony broke into its separate parts. That perfect symmetry we lost might have left behind a ghost. Theory 13 introduces us to the action, a hypothetical particle born from a quest for cosmic balance. While we have been searching for heavy, exotic particles to explain dark matter, the action proposes the opposite. It could be unimaginably light, billions of times less massive than an electron, and staggeringly abundant. Its origin story is tied to a subtle flaw in our understanding of the strong nuclear force. According to theory, this force should violate a symmetry known as CP, which would make particles like the neutron have a measurable electric dipole moment. Experiments, however, show no such thing. The neutron is perfectly balanced. To explain this unexpected symmetry, physicists proposed a new field that would correct the imbalance, and the quantum of that field is the action. In the fiery dawn of the cosmos, this action field would have been set into motion, oscillating like a pendulum swinging to find its rest position. As it settled, it would have filled the universe with a cold, coherent sea of these ghostly particles. Unlike the frenzied quarks in the hot plasma, actions would have been born cold and slow-moving, a form of cold dark matter from the very beginning. They would not interact with light or ordinary matter in any significant way, flowing through planets and people as if they were not there. Yet their collective gravity would have been immense. This invisible sea would have been among the very first non-baryonic structures, providing the gravitational scaffolding upon which the visible universe later assembled. Picture the formation of the first galaxies not in empty space, but within a vast, gentle current of these actions, their subtle pull guiding ordinary gas and dust into the luminous structures we see today. While we have yet to detect a single action, their theoretical elegance and potential to solve two great puzzles at once, the strong CP problem and the nature of dark matter, make them a compelling candidate for one of the universe's first and most fundamental shadows. Grand unified theories take the dream of a single law even further, suggesting a moment of even greater unity. These theories, often called GUTS, propose that the electromagnetic, weak, and strong nuclear forces were not just separate siblings, but were once a single grand force. In the universe's first trillionth of a second, this unified force would have governed every interaction, and its existence predicts the creation of a truly exotic relic, a particle with a property we have never seen in nature, an isolated magnetic charge. This is Theory 14, the magnetic monopole. Every magnet you have ever held, from a simple fridge magnet to the Earth itself, has both a north and a south pole. Cut a bar magnet in half, and you do not get an isolated north and an isolated south. You get two smaller magnets, each with its own pair of poles. A magnetic monopole would break this rule completely. It would be a particle that is a pure north pole or a pure south pole, a fundamental magnetic charge, just as an electron is a fundamental electric charge. According to grand unified theories, these monopoles would have been monstrously heavy, perhaps 1,000,000 billion times more massive than a proton, and they should have been forged in staggering numbers during the phase transition when the grand unified force broke apart, as defects in the cooling cosmic fabric, like cracks forming in ice. The problem is, if they were created in such abundance, their immense mass would have overwhelmed the universe. They would have dominated the density of the cosmos, causing it to collapse long before stars could ever form. We do not see this. In fact, despite decades of searching, not a single confirmed magnetic monopole has ever been detected. Their scarcity is one of cosmology's great puzzles, known as the monopole problem. The solution, once again, points to cosmic inflation. If that brief period of hyper-expansion occurred right after the GUT phase transition, it would have stretched space so dramatically that the density of these monstrous particles was diluted to virtually nothing. The entire observable universe might contain only a handful of them, lost in the vast cosmic ocean. So, in a fascinating twist, magnetic monopoles could indeed be among the very first particles, primordial titans born in the first flash of creation. But inflation, the same mechanism that planted the seeds for galaxies, also swept these relics away, hiding them from view and making their discovery one of physics' greatest ongoing quests. The scarcity of those primordial magnetic titans hints at a cosmos far stranger than a single, isolated bubble. If inflation stretched our universe from a quantum seed, what else did it create? This brings us to Theory 15, the multiverse and the principle of anthropic selection. Our universe, with its specific set of particles and finely tuned laws, may not be a unique creation. It could be one bubble in an endless, frothing sea of universes, a cosmic foam where each bubble has its own random draw of physical constants. This is the inflationary multiverse. Picture our cosmos not as the universe, but as a universe. When the inflattened field drove that hyper-expansion in our patch of reality, it may have done so unevenly, like water boiling in a pot. Regions where the field's energy dropped stopped inflating and cooled into stable bubbles, becoming separate universes like our own. But in other regions, the inflation never stopped, continually spawning new bubbles forever. Each of these bubble universes crystallizes with a random configuration of the fundamental forces. In one, the strong nuclear force might be slightly stronger, binding all quarks instantly into heavy, inert clumps. In another, electromagnetism could be weaker, preventing atoms from ever forming. The specific cast of characters, the quarks, electrons, and photons that make up our world, are just one possible ensemble in an infinite cosmic repertoire. So what does this mean for the first particles of our particular story? They were not preordained. They were a random roll of the dice, a lucky draw from a cosmic lottery of possibilities. The quark-gluon plasma that filled our infant cosmos had the properties it did purely by chance. This leads to a profound, almost philosophical, conclusion known as the anthropic principle. We find ourselves in a universe with stable atoms, long-lived stars, and complex chemistry not because it's special, but because it's habitable. Universes with different particles or forces likely cannot give rise to observers at all. We are here to ask the question precisely because our cosmic lottery ticket was a winner. The first particles of our existence, then, are not just the seeds of matter. They are the signature of a universe that won the jackpot, allowing the story of galaxies, planets, and life to unfold in the first place. While the multiverse suggests a cosmic lottery, our own universe holds a tangible relic from its fiery youth. Among the very first particles to break free and roam, the cosmos were not quarks or photons, but something far more elusive, the neutrino. This brings us to Theory 16, and a specific chapter known as the Lepton epoch. Just 1 second after the beginning, the universe had cooled enough for protons and neutrons to form, but it was still a blindingly hot, dense soup. For every proton, there were roughly a billion photons, and nearly an equal number of these ghostly neutrinos. They were everywhere, flooding the opaque cosmos in a relentless torrent. Neutrinos are nature's most aloof particles, interacting only via the weak nuclear force and gravity. In those first moments, they were constantly colliding with electrons and other particles, trapped in the thick plasma. But as the universe expanded and thinned, their chance to interact dwindled. Just 1 second after the Big Bang, when the cosmos was about the density of water, something pivotal happened. the neutrinos simply stopped seeing the rest of the universe. They decoupled, flying free in straight lines, never to significantly interact with matter again. In that instant, a snapshot of the 1-second-old universe was frozen into a sea of particles, creating the cosmic neutrino background. This background is older and more pervasive than the cosmic microwave background light we detect. It is a whisper from a time before atoms, before nuclei, even before the first stable atomic particles had fully settled. Today, trillions of these primordial neutrinos from the first second are streaming through your body every single second, silent witnesses to the universe's birth. They are not theoretical. We detect neutrinos from the sun and supernova regularly, but catching these specific ancient ones is a monumental challenge. Their energy is so incredibly low that they slip through our most sensitive detectors like ghosts through walls. Yet the hunt is on, with experiments using ultra-pure, super-cooled materials hoping to catch the faintest tremor from a neutrino that has been traveling for over 13 billion years. To detect this background would be to touch the universe at 1 second old, to feel the texture of reality when everything was still an incandescent, searing forge. It is a direct line back to the lepton era, a time when these faint, nearly massless particles ruled the cosmos. The neutrino's silent journey began in a cosmos already facing a profound theoretical crisis. Supersymmetry's elegant partnership promised to solve deep mysteries, but it also introduced a new and potentially catastrophic character to the cosmic drama. This is Theory 17, the gravitino problem. If supersymmetry is true, then every known force carrier must have a superpartner. The graviton, the hypothetical particle that carries the force of gravity, would be no exception. Its partner is the gravitino, a particle that blends the properties of a force carrier and a matter particle in one. The gravitino's theoretical existence is a beautiful mathematical consequence, but its practical implications for the early universe are anything but simple. Its story presents two starkly different endings, and our universe's survival depended on which one played out. In the first scenario, the gravitino is the lightest supersymmetric particle, stable and nearly impossible to destroy. Created in abundance in the hot Big Bang, it would have simply stayed. It would not interact with light or ordinary matter, streaming through the cosmos as a perfect candidate for dark matter. Another ghost from the first second helping to sculpt the galaxies. But there is a second, more dangerous possibility. What if the gravitino is not the lightest? What if it is heavy and unstable? In that case, these primordial gravitinos would have decayed sometime after the first few minutes of the universe, during the crucial period of Big Bang nucleosynthesis when the first atomic nuclei were forming. Their decay would have injected a tremendous burst of high-energy radiation into the delicate primordial soup. This would have been like throwing a grenade into a watchmaker's workshop. The violent showers of particles from decaying gravitinos would have smashed apart the fragile deuterium and helium nuclei as they were trying to assemble. The predicted abundances of light elements that we so precisely observe in the oldest parts of the universe would have been completely ruined. The fact that we see the exact amounts of hydrogen, helium, and lithium that the standard Big Bang model predicts tells us this did not happen on a large scale. Therefore, gravitinos, if they existed in the early universe, had to be either incredibly scarce or incredibly stable. This is the gravitino problem, a powerful constraint that forces theorists to shape their supersymmetry models very carefully. It is a stunning example of how the hypothetical first particles are not just abstract ideas. They are active players in a historical narrative. Their imagined properties dictate the conditions of the ancient cosmos, and the universe we see today is the forensic evidence that tells us which stories could possibly be true. The gravitino's potential to either build dark matter or destroy nucleosynthesis shows that the first moments were a razor's edge, a balancing act where the nature of a single, unseen particle could have rewritten our entire cosmic history before it even truly began. The Higgs boson's discovery felt like a final answer, but some physicists suspect it is a signpost pointing to a deeper truth. Theory 18 introduces us to Technicolor, a radical reimagining of how particles gain their mass. In our standard story, the Higgs field is a fundamental entity, a cosmic molasses that gives mass to particles as they move through it. But what if the Higgs is not fundamental at all? Technicolor proposes that the Higgs boson is not an elementary particle, but a composite, a bound state of something new. Just as protons are made of quarks, the Higgs could be made of technoquarks, held together by a new, powerful force called the Technicolor force. This force would be a near-perfect copy of the strong nuclear force, but operating at an energy scale 1,000 times higher. In the first instance of the universe, before the electroweak phase transition, this Technicolor force would have been dominant. The cosmos would have been filled with a seething plasma of these technoquarks and their force carriers, technigluons. They were the first actors on this alternative stage. As the universe cooled, the Technicolor force triggered its own phase transition. The technoquarks, once free, bound together into composite particles, including one that looked and behaved exactly like the Higgs boson we detect. In this view, the origin of mass is not a gentle slowing in a pervasive field, but a dramatic binding event, a cosmic condensation from a higher energy reality. The familiar particles we know gain their mass by interacting with this composite object, not a fundamental one. It is a compelling idea because it mirrors nature's own patterns, finding elegance in composition rather than new, unexplained fundamentals. While the simplest Technicolor models have faced challenges from precise experimental data, the core idea remains powerful. It suggests our universe's mass may have been forged in the furnace of a hidden strong force, a secret symmetry operating at energies so high we can only see its shadow in the particle we call the Higgs. The gravitino's delicate balance reveals how fragile our cosmic history might have been. Yet another idea suggests our entire universe is the product of a far more violent and profound transformation. Theory 19, the black hole universe hypothesis, proposes a truly nested reality. What if our entire cosmos, with all its galaxies and stars, exists inside a black hole belonging to a much larger, parent universe? In this mind-bending scenario, the Big Bang was not a beginning from nothing. It was a rebirth. The singularity at the heart of a black hole in that parent cosmos, a point where matter is crushed to infinite density, did not mark an end. Instead, it became the starting point for an entirely new space-time, our own. When matter and energy from the parent universe crossed the event horizon and fell toward that central singularity, they were not destroyed. According to some interpretations of quantum gravity and loop theory, the information they contained was transformed, their energy rebounding into a new, expanding dimension. Our universe's first particles, then, would have a profound and strange lineage. They would be the quantum remnants, the scrambled and reconstituted information of whatever stars, planets, or energy fell into that primal black hole eons ago. The quark-gluon plasma that filled our infant cosmos could be seen as the ultimate recycling project. The ashes of an older reality forged anew in a furnace of unimaginable gravity. This creates a dizzying, fractal picture of existence. Every black hole that forms in our universe could, in turn, be the seed for a brand new cosmos within it, bubbling into existence with its own laws and particles. We could be living inside one link of an infinite chain, a cosmic matryoshka doll where universes are born within the darkest objects we know. It is a hypothesis that elegantly sidesteps the mystery of the initial singularity by giving it a physical origin in a larger reality. The first light of our Big Bang was not the first light of all creation, but the transformed glow of a universe that came before, shining through the veil of a singularity. That cosmic matryoshka doll of black hole universes hints at a hidden structure to space itself. But what is that structure made of? We must return to the loops. In Theory 20, the spin networks of loop quantum gravity, we find the universe's most fundamental blueprint. Forget empty space as a smooth, blank stage. At the tiniest imaginable scale, the Planck scale, space is not a void. It is a dynamic, shimmering web of relationships, a tapestry woven from threads of pure geometry. These threads are the loops of gravitational field, and their intersections create a structure known as a spin network. Picture a vast, three-dimensional graph, like an impossibly complex molecular model or a cosmic neural network. Each line or edge carries a label, a quantum number that represents a tiny, discrete unit of area. Each point where lines meet, a vertex, represents a tiny, discrete unit of volume. This is not a graph drawn in space. This graph is space. The entire geometry of the cosmos, its shape and curvature, is encoded in the connections and labels of this ever-changing web. Now, rewind time to the very beginning. In this view, the Big Bang is not a point of infinite density, but a moment where this spin network was at its maximum possible density, a highly interconnected, buzzing hive of quantum geometry. The first particles, the quarks and electrons that would later fill the plasma, were not separate things injected into this space. They were excitations, vibrations, or even defects within the spin network itself. Imagine a single, specific pattern of extra energy or a kink propagating along the threads of this cosmic web. That localized vibration, that defect in the perfect geometric lattice, could manifest as a particle with mass and charge. The different ways the network can vibrate could give rise to the different properties we see in the particle zoo. In the furious heat of the first moments, this network would have been a chaotic storm of such excitations, a quantum foam of geometry buzzing with potential particles. As the universe expanded and cooled, the network evolved, its connections simplifying, and those buzzing excitations settled into the stable, resonant patterns we recognize as the first generation of fundamental particles. So in this breathtaking picture, the building blocks of matter are not separate from the fabric of space. They are melodies played on the strings of spacetime itself, a symphony written directly into the quantum code of reality. The idea that particles are melodies played on spacetime's strings leads to a truly radical question. What if the stage itself is also an illusion? Theory 21, the emergent gravity paradigm, proposes that gravity, and perhaps even the very fabric of spacetime, is not a fundamental force. It is not woven into the universe's foundation. Instead, gravity emerges, a collective phenomenon that arises from the interactions of something far more basic, like a wave emerging from the motion of countless water molecules. In this view, the cosmos did not begin with gravity already in place. It began with a seething, chaotic sea of quantum information, a vast network of simple, interacting bits. These quantum bits, or qubits, had no inherent sense of space or time. They were simply connected to one another, exchanging information in a tangled web of relationships. The first particles of our story were not particles at all, but these fundamental informational links, buzzing in a state of pure quantum potential. As this network cooled and settled, something remarkable happened. A pattern crystallized from the chaos. The way information flowed between these quantum bits began to create the illusion of a continuous, smooth geometry. The collective behavior of the system made it look and feel as if there were three dimensions of space and one of time. Gravity, in this picture, is not a force that travels through spacetime. It is a side effect, a consequence of the way information is distributed and processed across this underlying quantum network. Think of a hologram again. The three-dimensional image you see is not fundamental. It emerges from the data encoded on the two-dimensional surface. In emergent gravity, our entire four-dimensional universe of spacetime and matter is the holographic projection, and the quantum bits are the code on the boundary. Or consider a more tangible analogy, the temperature of a glass of water. You can feel it as warmth, But zoom in to the molecular level and that concept disappears. There are only water molecules jiggling and colliding. The temperature is not a property of any single molecule. It is a statistical description that emerges from their collective dance. Gravity could be exactly the same. The smooth curvature of spacetime described by Einstein is the temperature, the large-scale effect we perceive. But at the Planck scale, there is no smooth curvature, only a frenzied quantum dance of information bits. So what does this mean for our origin story? In the first moments, the universe was not a point in spacetime. It was a maximally entangled, densely connected quantum state. As it evolved, this state cooled, and from its complex interactions, the familiar concepts of locality, distance, and finally gravity itself condensed into existence. The quark-gluon plasma did not form in a pre-existing gravitational arena. The arena and the actors emerged together from a deeper, more fundamental layer of reality, a cosmic phase transition where the universe learned to be a place. This slight residue of matter is the only reason you exist. The universe's first great annihilation should have left nothing behind. For every particle of matter born in the fiery dawn, an equal and opposite particle of antimatter should have been created. When matter meets antimatter, they annihilate in a flash of pure energy, leaving nothing. So why, after that primordial inferno cooled, was there anything left at all? Why did a single quark survive for every billion that were destroyed? This is Theory 22, the baryogenesis puzzle, and its solution is written into the very first moments of our cosmos. The standard model of particle physics, for all its power, predicts a perfectly symmetrical creation. The Big Bang should have produced equal amounts of matter and antimatter, leading to total mutual annihilation. We would live in a universe of empty, fading light. The fact that we are here, that stars and planets and people exist, is proof that something broke that perfect symmetry. Something tipped the scales. Physicists call this process baryogenesis, the genesis of baryons, the class of particles that includes protons and neutrons. For it to happen, three conditions outlined by the physicist Andrei Sakharov had to be met in the early universe. First, there had to be a process that violated the conservation of baryon number, meaning it could create more matter than antimatter. Second, the laws of physics had to treat matter and antimatter slightly differently, a violation of something called CP symmetry. And third, these processes had to occur out of thermal equilibrium, away from the smooth, uniform heat of the plasma. One leading candidate for how this happened is a theory called leptogenesis. It proposes that the imbalance did not start with quarks directly, but with their lighter cousins, the leptons, like neutrinos. In the searing heat of the first fraction of a second, incredibly heavy, hypothetical particles known as right-handed neutrinos could have been created. As these heavy neutrinos decayed, they did so in a way that subtly favored the production of regular matter particles over antimatter particles. This tiny bias, a 1 part in a billion preference, was then transferred through other interactions into the quark sector. Imagine a vast, cosmic coin toss happening a trillion times. A perfectly fair coin would land heads and tails equally, but if the coin was ever so slightly weighted over countless flips, a small but decisive excess of heads would emerge. Leptogenesis suggests the early universe had such a weighted coin. The result was a universe where for every billion antiquarks annihilating with a billion quarks, one single quark was left behind, with no partner to destroy it. That 1 in a billion survivor is the hero of our entire story. Every proton in every atom in your body is a direct descendant of that minuscule excess. The first particles that truly mattered, in the most literal sense, were those survivor quarks. They were the precious residue that avoided annihilation, the raw material that escaped the cosmic furnace to eventually cool, bind into protons and neutrons, and build a world made of something rather than nothing. The search for the mechanism behind this is ongoing. a hunt for subtle cracks in the mirror of nature that allowed our universe to be born from a broken symmetry. That one-in-a-billion survival story left the cosmos with a precious, but sparse, sprinkling of matter. Yet another form of matter, far more abundant and mysterious, was also taking shape in those first moments, not from annihilations but from gravitational collapse. Theory 23, the primordial black hole scenario, proposes a radical origin for dark matter. These are not the black holes we know, born from the violent deaths of massive stars. Primordial black holes, or PBHS, would have formed directly from the fabric of the infant universe itself. In the first second after the Big Bang, the cosmos was not perfectly smooth. It was imprinted with those quantum ripples from inflation, regions of slightly higher and lower density. In the most extreme over-dense regions, the pressure of the hot radiation and matter could not overcome the pull of their own gravity. A knot of space-time could simply pinch off, collapsing directly into a black hole. This could happen long before the first stars ever flickered into existence, within the first second of cosmic history. These objects would be true fossils, the first macroscopic structures to emerge from the quantum foam. They range in size from the microscopic, with the mass of an asteroid compressed into a space smaller than an atom, to the monstrous, with masses rivaling thousands of suns. And in a gravitational sense, they behave exactly like particles. They are discrete, localized packets of mass that interact with the rest of the universe almost exclusively through their gravity, streaming through space and weaving the cosmic web, just as dark matter is theorized to do. Picture the quark-gluon plasma not as a uniform soup, but as a churning ocean with occasional, terrifying whirlpools. Where the density spiked just enough, a whirlpool would form, its gravity so intense that not even light could escape. It would vanish from the visible universe, leaving behind only its gravitational shadow. This shadow could then attract the ordinary matter around it, acting as a seed for the first galaxies. If PBHS exist in sufficient numbers, they could account for all or a portion of the dark matter that binds our cosmos together. They are a haunting possibility that the universe's missing mass is not an exotic new particle, but a vast population of ancient, invisible holes, born from the first tremors of creation and hiding in plain sight ever since. The universe's matter-antimatter asymmetry is a profound puzzle. But what if the solution involves not just a broken symmetry, but a hidden reflection? Theory 24, mirror matter, proposes a cosmos with a perfect yet invisible twin. This idea suggests that for every particle in our standard model, there exists a duplicate, a mirror particle, governed by an identical set of forces that operate in a parallel sector of reality. Think of it as two identical cosmic houses built side by side, but with no doors or windows connecting them. The inhabitants of each house go about their lives, completely unaware of the other, except for one thing: they can feel the faint rumble of each other's footsteps through the shared foundation, gravity. In the earliest, hottest moments, the two sectors were not so separate. They were in thermal contact, their particles interacting through some high-energy bridge that has long since sealed shut. Both our familiar quark-gluon plasma and an identical, seething mirror quark-gluon plasma filled the same space, two symphonies playing simultaneously in the same hall. As the universe expanded and cooled, that bridge collapsed. The two sectors decoupled, and the mirror particles ceased to interact with ours via any force except gravity. They became ghostly counterparts, streaming right through our world as if it were not there. This makes mirror matter a compelling candidate for dark matter, an entire hidden universe of particles with mass, woven into the fabric of our own but forever out of reach. So the first particles of our cosmic story were not a single cast. They were a double ensemble. For every quark that condensed from our plasma, a mirror quark condensed from its own. For every photon that began to race freely, a mirror photon did the same in its parallel realm. The dawn of matter was a dual birth. We exist in one half of that creation, seeing only our own light, feeling only our own forces, while the gravitational shadow of our cosmic twin pulls silently on the galaxies, shaping the cosmos from behind a veil we may never lift. The idea of a hidden cosmic twin is dizzying, but it still assumes a stage for the drama to unfold. What if the stage itself is not a smooth continuum, but something far more sparse and logical? Theory 25, causal set theory, proposes a universe built not from stuff, but from pure relationship. In this view, spacetime is not a fundamental fabric. It is a secondary, emergent property that arises from something more basic, a vast collection of discrete events linked by cause and effect. Imagine the entire history of the cosmos, every single happening from the first quantum flicker to the reading of this sentence as a set of individual points. Now, connect these points with arrows. An arrow points from event A to event B if A can influence B, if A is in the past light cone of B. This creates a vast, growing network of causal relationships, a structure mathematicians call a partially ordered set. This is the causal set. It is the skeleton of reality, stripped of any preconceived notions of distance or duration. The smooth, four-dimensional spacetime of our experience, with its intervals of space and time, is a coarse-grained approximation that emerges when you look at this network from a distance, much like a smooth fabric emerges from the weave of individual threads. So how does such a universe begin? It grows. The causal set is not static. New fundamental events, new points are born. They appear in relation to the existing network, finding their place in the web of cause and effect. The very first particles of our cosmos, then, were not vibrating strings or quantum loops. They were the earliest elements in this growing causal set, the first few points to appear. Their relationships, the very first causal links drawn between them, defined the nascent structure of spacetime itself. There was no space outside for them to exist in, and no time before for them to appear. The act of their coming into being, and the causal connections they established with each new arrival, created the first notions of before and after, here and there. Picture a single point appearing, then another. If the second can be causally influenced by the first, a link is drawn. This is the universe's first moment, its first tick of causality. As more points are added, the network blossoms. Regions with a high density of points and links become areas of high gravitational curvature, like the heart of a galaxy. Sparse regions become the vast cosmic voids. In this breathtakingly minimalist picture, everything we see and feel, from the force of gravity to the passage of time, is a story told by the pattern of connections in an immense, growing graph of cause and effect. The quark gluon plasma, the inflationary expansion, all of it is the rich, emergent narrative written in the language of a fundamentally discrete and causal universe. The stark logic of causal sets gives way to a concept that defies our most basic intuition about matter. Theory 26 introduces us to the utterly bizarre world of unparticle physics. This speculative idea, born from the mind of physicist Howard Georgi, proposes a hidden sector of reality that does not play by the standard rules. In our familiar world, particles come in discrete packages with specific masses. An electron has one mass, a quark another, like distinct notes on a piano. Unparticles are different. They are not a set of notes, but a continuous hum, a spectrum of possibility with no definite scale. Imagine trying to describe the sound of ocean waves. You could not point to a single, specific frequency that defines the roar. It is a blend, a scale-invariant phenomenon that sounds similar whether you are near the shore or miles away. Unparticles are the cosmic equivalent of that roar, a form of stuff that does not crystallize into individual particles with set properties. If such a sector existed in the early universe and interacted even weakly with our own, its influence would have been profound. During the extreme energies of the first moments, the unparticle sector and our standard particle sector could have been in communication. As the cosmos cooled and underwent its phase transitions, the unparticle sector would have decoupled, but not before leaving ghostly fingerprints on processes like the formation of the first nuclei or the distribution of the cosmic microwave background. Its scale-invariant nature means it would have behaved the same way across a vast range of energies, acting as a smooth, continuous background field against which our chunky, discrete particles condensed. In this view, the very first stuff might not have been particulate at all. Before quarks, before even the quantum foam of spacetime, there could have been this unparticle continuum, a primordial essence without fixed form or mass, a cosmic canvas upon which the concept of a particle was only later painted. It is a reminder that our categorization of reality into neat, countable pieces might be a convenience of our cooled-down universe, a simplification that hides a deeper, more fluid and mysterious origin. That unparticle hum suggests a fluid, continuous beginning, but another theory brings us back to a moment of ultimate compression, a bounce instead of a bang. Theory 27, the Planck star and quantum bounce, refines the idea of a cyclical cosmos with a specific, stunning mechanism. Inside a black hole, or at the origin of our own universe, matter may not collapse forever into an infinitely dense point. Instead, when it reaches the maximum possible density allowed by quantum gravity, a pressure arises from the very fabric of spacetime, creating a powerful repulsive force. This is the quantum bounce. The collapsing matter hits this fundamental wall and rebounds, like a spring compressed to its absolute limit. The result of that rebound is a Planck star, a hypothetical object of unimaginable density, but not infinite. It is a universe in its most compact, embryonic state. In this model, our Big Bang was not the beginning of time. It was the moment of that great rebound, the instant the previous contracting phase reached its minimum size and began to expand anew. So what were the first particles of our cosmic chapter? They were the quantum remnants of the previous collapse, the very same matter and energy that had been crushed to the brink of oblivion, now rebounding outward with tremendous force. Visualize a massive star at the end of its life, its core collapsing inward under its own gravity. In our standard story, it forms a black hole with a singularity at its heart. But in the quantum bounce scenario, that infalling matter does not vanish into a point. It compresses until the repulsive quantum pressure of spacetime itself becomes overwhelming. The collapse halts, reverses, and the star's core bounces back, exploding outward as the seed of a new expanding region. Our entire observable universe could be the interior of such a rebounded core. The quark-gluon plasma that filled our infancy was not created from nothing. It was transformed. It was the superheated, re-energized debris of a prior cosmic phase, given a second chance to expand and cool into galaxies and stars. This offers a profoundly different vision, a non-singular beginning where the universe has a finite minimum size, avoiding the mathematical infinities that plague the classic Big Bang model. The first light of our cosmos was not the first light of all creation, but the rekindled glow of a universe that had previously grown cold and dense, now bursting forth again from the quantum resilience of spacetime itself. The resilience of a quantum bounce offers one origin for our cosmos, but the universe's first moments also forged a shadow that has never been seen. Among the most compelling candidates for that shadow are the weakly interacting massive particles, or WIMP. Their story is not one of cosmic rebirth, but of a perfect thermal freeze-out. In the searing heat of the universe's first microseconds, energy was so abundant that particles of all kinds were constantly created and destroyed in pairs. This included hypothetical WIMP and their antiparticles, colliding and annihilating in a frenzied equilibrium with photons and quarks. They were a natural part of the primordial plasma. But as the universe expanded and cooled, a critical threshold was crossed. The temperature dropped to a point where the energy of collisions was no longer sufficient to create new WIMP pairs. The annihilation continued, but the creation stopped. The WIMP began to vanish, annihilating each other away. However, the expansion of space itself saved them. As the cosmos swelled, the WIMP were spread so far apart that they could no longer find each other to annihilate. Their numbers were frozen, locked in at a relic density that remains constant to this day. This process is called thermal freeze-out, and its mathematical elegance is what physicists call the WIMP miracle. When you plug plausible numbers for a WIMP mass and interaction strength into the equations of the early universe, the predicted leftover abundance matches almost perfectly with the amount of dark matter we observe through its gravitational effects. It is as if the cosmos left us a receipt, and the numbers line up exactly. So in this view, the dark matter that sculpts galaxies is not an exotic afterthought. It is a fossil, a thermal relic from the same fiery forge that made the first quarks. These particles were once in thermal equilibrium with everything else, a normal part of the cosmic family, before the expanding universe isolated them forever. They represent a ghostly population of first particles that decoupled from the light of creation, and have been streaming through the cosmos, unseen and untouched, for over 13 billion years. The hunt for them continues in deep underground laboratories, where scientists wait in profound silence, hoping to catch the faintest tremor from a WIMP that has been wandering in the dark since the universe's first second. The WIMP miracle offers a thermal origin for dark matter. But what if the very properties of all particles were set by the shape of hidden realms? The geometry of the cosmos might extend far beyond the 3 dimensions we move through. Theory 29 takes us into the hidden architecture of string theory, where the universe's first particles were sculpted by the form of extra dimensions. In frameworks like string theory and M-theory, reality is not 3-dimensional, but exists in 10 or 11 dimensions. The reason we only experience 3 spatial dimensions is because the others are curled up, or compactified, into shapes so incredibly tiny that they evade our perception, existing at every single point in our familiar space. The specific shape of these extra dimensions is not arbitrary. They are theorized to be intricate, multi-dimensional forms known as Calabi-Yau manifolds. Think of them as the microscopic, complex machinery inside every point of space, like the intricate clockwork inside a watch's smooth face. The size and shape of this hidden geometry, called the moduli, determine everything about the particles we see. How a fundamental string vibrates as it moves through our 3 large dimensions is directly constrained by how it can also wind around and vibrate within these tiny, curled-up Calabi-Yau spaces. One specific vibrational pattern might correspond to an electron, another to a quark, with their mass and charge dictated by the precise geometry they are moving through. In the unimaginable heat of the universe's first moments, this situation was fluid and chaotic. The extra dimensions were not stable. They could have been dynamic, fluctuating in size and shape, with the moduli fields themselves evolving wildly. The first particles, the vibrational modes of strings, would have been in a state of constant flux, their properties shifting as the hidden geometry breathed and changed. There was no fixed electron or quark, only a spectrum of possibilities. Then, as the universe expanded and cooled, it underwent a series of cosmic phase transitions. The extra dimensions stabilized. They settled into a specific Calabi-Yau shape, and the moduli fields found their lowest energy state, locking into place. It was as if a turbulent, molten metal suddenly cooled and crystallized into a rigid lattice. That crystallization froze the vibrational possibilities of strings into a fixed set of resonant patterns. The particle spectrum we observe today, the entire cast of characters in the Standard Model, was effectively locked in by that geometric freeze. The first stable particles were not born from a cooling plasma alone, but from the settling of a hidden, higher dimensional landscape. This means the charge of an electron, the mass of a quark, and the very number of particle generations might be cosmic accidents. the result of which specific Calabi Yau manifold our pocket of the multiverse randomly settled into as it cooled. The universe we inhabit, with its specific laws and particles, is a direct reflection of a geometry we cannot see. A silent, six-dimensional sculpture that has dictated the rules of reality since the first fraction of a second. That hidden geometry may not be fixed, but born from a process of cosmic simplification. Our final theory, number 30, is quantum graphity, a model where space itself is not a stage, but a living, evolving network. In this radical picture, the newborn universe did not have three dimensions. It began as a state of pure connection, a dense, tangled web where every single fundamental node was linked to every other. Mathematicians call this a complete graph, a buzzing hive of total connectivity. There was no concept of distance or direction here, only relationship. Everything was equally close to everything else, a state of ultimate unity and chaos. Then, as this proto-universe cooled, it underwent a phase transition. The connections or links between nodes began to freeze and break in a specific pattern. Think of a vast, hot crowd of people all holding hands with everyone else. As the temperature drops, they cannot maintain every single grip. They let go of most connections, settling into a stable pattern where each person holds hands only with their immediate neighbors. This new, sparser arrangement creates a clear sense of order, of who is near and who is far. In quantum graphity, that is exactly how our three-dimensional space was born. The breaking of links crystallized the network into a regular, lattice-like structure. And that lattice is the fabric of space we move through. The dimensions we experience are not fundamental. They are emergent properties of how this graph is connected. So where do particles fit into this graph? They are not separate things placed onto the lattice. They are excitations, defects, or vibrations within it. A localized kink or a wave propagating along the links of this cosmic graph could manifest as a particle with mass and charge. An electron might be one specific pattern of disturbance humming across the network, while a quark is another. In the beginning, when the graph was maximally connected, these excitations would have been wild and undefined, a chaotic buzz with no stable form. But as the graph cooled and settled into its three-dimensional lattice, the possible vibrations stabilized into the discrete set of patterns we recognize as the fundamental particles. In this breathtaking view, the first particles and the space they inhabit did not appear in sequence. They co-evolved from the same underlying substance, a network of pure relationship. The quark-gluon plasma did not form in a pre-existing arena. The arena and the actors emerged together from the freezing of a graph, a cosmic crystallization where the universe found its structure, and in doing so, defined what could exist within it. It suggests that at the most fundamental level, reality may be nothing more and nothing less than a vast and dynamic web of connections, learning to be a place. From the searing plasma of quarks to the silent geometry of spin networks, we have journeyed across 30 frontiers of human imagination. Each theory, from the well-trodden path of cosmic inflation to the wild frontiers of holographic projections and quantum bounces, represents a different answer to the same profound question. What is the fundamental note from which the symphony of reality is composed? Is it a vibrating string, a loop of space-time, a fluctuation in a quantum void, or a line in a cosmic code? This incredible diversity of thought is not a sign of confusion, but a testament to the grandeur of the mystery itself. The quest to understand the universe's first particles is far more than a technical puzzle for physicists. It is the deepest possible inquiry into the nature of existence. We are not just looking for a list of ingredients, we are searching for the recipe of reality, trying to read the first line of a story that has been unfolding for over 13 billion years. Every time we peer into a particle collider or study the ancient light of the cosmic microwave background, we are conducting an archaeological dig at the dawn of time, sifting through the ashes of creation for clues. Thank you for joining this cosmic thought experiment, or venturing to the very edge of what we know and gazing into the profound unknown. Now we turn the question to you. Which of these theories resonates most deeply with your sense of wonder? Was it the elegant symmetry of supersymmetry, the cosmic hologram, or the endless cycles of a bouncing universe? Share your favorite in the comments below. We would love to continue the conversation. If you enjoyed this deep dive into the origins of everything, please subscribe for more journeys to the heart of space's greatest mysteries. As you look up at the night sky tonight, remember this. Every photon that meets your eye, every atom in your body, carries within it the echo of that first unimaginable moment. You are not just living in the universe. You are a living remnant of its fiery birth, a conscious piece of the cosmos trying to understand